Now, good day, ladies and gentlemen. So today we are going to look at some definition of stochastic integral. So first of all, we need to understand what we mean by mean square convergence. And I am sorry for making this video late at night because I didn't have network during the day. So here it is. So for mean square convergence, I was still trying to explain that we say that xn converges to x in mean square if the limit of n goes to infinity of the expectation of xn minus x squared is 0. So we say that it means that xn converges to x in mean square, right? So meaning that we are able to find what again we can talk about x going towards x if we are able to know like this definition. So yeah, so this is the definition of mean square convergence. So if you know about this and you can try to make n as big as possible, again I'm like increasing the number of like interval in our case to go towards infinity, then we are able to then estimate what x is, what our real x is. And this, as it turns out, is going to be very important when you're doing stochastic integral, because when you're integrating, so we say that the integral of 0 to t of a function, or a function that depend on a Brownian motion, like w. In our case, let's just say like w. I can just add an f over here, f of w, a function of a Brownian motion, where again I'm like the integral of a function of a Brownian motion with respect to a Brownian motion. We can say that this function like converges to what it converges to this definition. So it converges to this. We say that it's going to converge. Actually, it's the other way around. We say that, I don't think this is the right notation. The sum j equals to 0 n minus 1 w, we have to add f of s j n, and then you're gonna say change j with respect to like w. So this w over here, you know it as just the interval as the length of the Brownian motion. I mean, like from one step to the next, right? So it's gonna be so you can just say change of j n of w is going to be w s j plus 1 n minus w s j n. So as you can see, this definition, its left side Riemann sum, right? So you are basically using the definition of Riemann sum to like find this definition to find what the integral is. So as you've known, like in calculus you can use Riemann sum, but in this case we are only using the left side Riemann sum, right? So if we have an interval like this, let's say start from 0, 1, 2, 3, 4, 5, and those are our n. We are going to use this to here, and then from there here, from there to here, there to here, there to here. So this is what happens, like, but then we cannot use the right hand side, we need to use the left hand side, because in theory you can even see that, because you cannot look at the future to predict this. Again, I'm like, to make conclusions about the Riemann integral. So you should always use the present to look at the future. So hence we start at j, not j plus 1. So we need to start from j and then go towards j plus 1. So with this being said, we can then conclude that if you are trying to integrate something, if you are trying to find the integral from 0 to t of f of ws dws, that is a function that is influenced by a Brownian motion, you can just find the limit as n goes to infinity of the Riemann integral. Change in the Brownian motion. So basically if you want to know, again, if they ask you this question, you are able to just look at this part and then make a conclusion about it. So in your notes or everywhere, I think you will be given some sort of like results, or they might, I mean, like, actually, as a matter of fact, you are required to know some results, because I don't think they will give you the results, or at least all of them. And one of those results is, of course, like, if you again, so these are just results, right? They are not necessarily the stochastic integral, but they are results of the Riemann integral. I think it's called Riemann-Stieltje integral. So results, not resulting. Some important results that you can use, I think, but one of them is the limit as n goes to infinity of the sum of n minus 1 j equals to 0 of like w as j plus 1 and w as n of j, right? I think if they square this, then you are able to say this thing goes to t, basically. So when you are, okay, I mean, like, when you are trying to like find the integral, you are better off using this in your equation. I mean, obviously you do not have this somewhere. I'm like, they are not the same, because this one over here is squared, so try to find a way you can make it squared. And normally what they use and what they would give you, but what I would encourage you to just remember in the test is this, is that a b minus a is just going to be 1 over 2 b squared minus a squared minus 1 over 2 b minus a squared minus a squared, everything squared. Let me just put this very well. So as you can see from this side, if you can, so basically if you have a, I mean, like, which happens to be like our w of j, the WSJ, even this one's gonna be WSJ. So when you are looking at like something that has this in its equation, or later, let's say maybe you are looking at the integral of ws, right? dws. So you are better off using this, because you already have a result that you can use, or that is easy to prove, at least. I don't remember if you can just do it directly. I think you can still do it directly, but like looking at it this way, you are better off. So this is what happened in Riemann. Some again, I'm like wave of the mean square convergence. So if you are able to find this, if you can find the part that I'm going to highlight using your Riemann, or let me just say this part. If you're able to find that part, then you are able to find the integral. So you can conclude that, okay, this is the same as our integral. So yeah, let me check if I have anything else. Here, I think from there on, you can just look at some, again, I'm like at some definitions, actually. I'm like at some calculations. Yeah, I hope this like helps you understand a little bit about Brownian motion for now. Okay, thank you.